expression that we were discussing yesterday. So I hope you understand. We were talking about ideal solutions in the binaries independently, and it's also possible that you may not have ideal solutions in individual binaries, but each of the binaries could behave non-ideally, but yet the non-ideality energy terms would cancel out, and you can have what is an ideal exchange, although individually the two minerals do not behave ideally. Right? But we also said that we will come back to this discussion of non-ideality later on, and we will see how things work out. Now, from here, if we go back to the original equation, it should read now 3RT. You know, I'm reverting back to the old equation, since I don't know the reactions from yesterday, which is with you. So it is RTLN XMG by XFE in biotite divided by XMG by XFE garnet, and this is equal to minus delta HR0 minus T del SR0 and plus P delta VR0. Recognizing that this term would be very small, the effect of this would be very small, because I told you in the last class, del V is equal to very small, and for low pressure, this is almost insignificant effect on the total energy term. So going back to the last expression, now we can write the full equation from which we came from. Del HR 0 minus T del SR 0 plus P into del VR 0 plus 3RT ln. Now this term here, I will refer to as what is called KB, or this is called D stands for distribution coefficient. Sometimes they are also called partition coefficient. That means this term dictates how Mg and Fe in the two sides will exchange depending upon the pressure temperature condition. So instead of writing this term, we can write RT ln Kd. There is a way to write it. You can write FeMg to say which cation partition, and above you could write biotite and garnet. So it would mean iron magnesium partitioning between garnet and biotite. So I will write the Kd term here in case you and me forget. It is nothing but XMG by XFE biotite versus divided by XMG by XFE in garnet. That's all what it is all about, and so we can erase this term now. So this is what is our Kd now, partition or the distribution coefficient. And then we had the other term as plus 3RT ln gamma Mg by gamma Fe biotite divided by gamma Mg by gamma Fe and garnet. There is a temperature term here, and this is in the brackets. So here we are now with the full expression as it was before is equal to 0. So that is what is the full equation that we did yesterday. Only thing what we have done is Kd, which is iron magnesium partitioning between biotite and garnet, we have just made it a designation, that's all. And this term is called the partition coefficient. And this term is now added, and we will see how this works. Now, this term can be now divided. You can see it is 3RT ln gamma Mg by gamma Fe garnet, a biotype, divided by gamma Mg by gamma Fe garnet. We can write this term as is equal to 3RT ln gamma Mg by gamma Fe biotypes minus 3RT ln gamma Mg by gamma Fe garnet. This term only. We are splitting the term into two. Now, I take you back to the original expression that was there, that RT ln, remember we did determine this, RT ln gamma A is equal to WAB into XB squared. Right? WAB into XB squared. Now, if we take this here, then what does it mean? This was for a binary where RT ln gamma A is equal to WAB and XB squared. In this, if we also assume regular solution model, then we will come to the expression. For example, this one will be 3RT if I take it right out of the whole thing. Then you have ln gamma Mg biotype minus ln gamma Fe biotype minus ln gamma Mg garnet minus ln gamma Mg gamma Fe garnet. Right? Now you can look at this here. Look at this term. So what will I write here is equal to 3 into RT ln gamma Mg. RT ln gamma Mg. So what will it be? Will be equal to WAB, WFEMG biotype into X. You see, this one was garnet Mg, so this will be XFE biotype whole squared. Can you see that? I've taken 3 out, and you have RT ln gamma Mg. RT ln gamma Mg should be equal to WFEMG into XFE biotype square. So similarly, this will be WFEMG biotype into XMG biotype whole square. Yes or no? So this will go into the first bracket. And then you have minus, same relationship, WFEMG, but this time it's for garnet. And this will be XFE garnet squared. This one will be another bracket. And minus WFEMG in garnet into XMG garnet squared, and the whole thing goes under the bracket. Tell me, have you understood it? Have you understood? Look at it again. RT ln gamma Mg minus RTL and gamma Fe biotite. Now let's look at one. RTL and gamma Mg by Fe biotite would be 3 RTL and gamma Mg biotite minus Ln gamma Fe biotite. Now what is RTL and gamma Mg biotite here? Mg biotite. This will be, according to this, WFeMg XFe biotite squared. This one will be WFeMg biotite XMg biotite squared, and similar for the garden. I give you 1 minute to look at it. So if you do this, then let's erase this. And what we can write from this now is equal to 3 as before, and put a bracket. And this will be WFeMg biotite into XFe biotite squared minus XMg biotite squared. Yes or no? Because if I take WFeMg out, then it should be XFe biotite squared minus XMg biotite squared. And this one then would be WFeMg garnet into XFe garnet squared minus XMg garnet squared. That's how it should be. If we do that, then if you remember, if you will understand, A squared minus B squared will be A minus B into A plus B. A plus B is what? That means XFe plus XMg biotite plus is equal to 1, because iron and magnesium are only two components. So XFe plus XMg should be equal to 1. So therefore, this expression then we could make it WFeMg into 1 minus 2XMg biotite. You see that? Why? Because XFe minus XMg into XFe plus XMg. XFe plus XMG is 1, but XFe is 1 minus 2XMg biotite. And this one is biotite. And therefore minus WFeMg garnet into 1 minus 2XMg garnet. This is what essentially it is. When we were talking that the solutions were ideal, this would mean the solutions, if the solutions, now a point here to note, if the solutions were individually ideal, as I said before, that means WFeMg biotite should be equal to 0 and WFeMg garnet should also be equal to 0. But if it's a case of ideal exchange, then none of them are equal to 0. That means none are ideal. But the net effect is equal to 0. This would be called an ideal exchange. So now, if we take this expression now, you see here this expression is the same as this. So I will delete this. I will also delete this. And I will delete this expression. and leave this one. So now I can write plus plus 3 into WFEmg biotite into 1 minus 2x mg biotite minus WFEmg garnet into 1 minus 2x mg. That's what I will write. It is the same as this one. Then, if I do this, then look at this term, T del SR0, and this term is also RT. This contains temperature, this contains temperature. The other terms here does not contain temperature. So, if I bring this term is equal to 0, yeah? So, if I take these terms with the temperatures, these terms, one term and two term on the other side of the equation, then we will have del HR 0 plus P del VR 0 plus 3 WFEmg biotite into 1 minus 2x mg biotite minus WFEmg garnet into 1 minus 2x mg garnet. But then I can divide it by del SR 0 minus 3R ln Kd, and here I write T is equal. This is my expression. You think about it. I give you a minute to, I have jumped a few lines, but I think it's not so difficult to understand. What I have done essentially is I kept this term, and this term at the same position and shifted T bearing terms on the other side and taken T out and written this. You check for the signs and all. So when I take these two terms, this becomes positive, this becomes negative. So positive and negative. And I've taken T out. So here is T. T is in kelvins. The important point here is two, namely this. One is this and one is this. These are the two important points. Remember, this Kd is this one. If we had ideal exchange, if we had no non-ideal effects, then this term would be non-existent. So we would have Pk is equal to del HR0 plus P del VR0 divided by del SR0 minus 3R ln, and if we place back XFE by XMG, then it should be XMG by XFE in biotite divided by xmg by xfe garnet. This would be the expression if there was no non-ideality. But if there is a non-ideality effect, and the non-ideality can be expressed in terms of a simple regular solution, then this would be the additional term in this expression. Now you see, another thing is P delta VR0. Now this term, as I have told you, the delta V value is normally very, very small. Very small. So if you are talking of low pressure conditions, then you can almost ignore this. It will be almost equal to 0. If you're working at low pressures and delta VR0 being small, this will have almost no effect. So in this expression, P delta VR will have almost no effect. And therefore, temperature then, if you look at the ideal mixing model, temperature then will be a function of the composition of the two phases. Or the composition ratio, the partitioning of iron magnesium between biotite and garnet is now therefore a function of temperature. So if you change the temperature, the Mg by Fe ratio will change. This is the same as we discussed with this expression. Same thing we discussed as this expression. So this is what is important at the moment, the point that I wanted to make, that element partitioning depends also on temperature, but if there is non-ideality in the system, then it's not only a function, partitioning is not only a function of temperature, but partitioning is also a function of temperature and composition. The effect of pressure is small. That is the point I'm trying to make here. So when we are talking crust-mantle relationship, element partitioning, we should have a good idea of what we are really looking into instead of just talking through certain terms. Otherwise, it's better to understand the meaning of it and therefore understand. Now, a small note before we go into the magnesium iron reaction. A small point to note here, maybe you may not have picked it up. In a temperature pressure diagram, let's say this is temperature and this is pressure. You know something called the Cloche. dP by dt is equal to delta SR divided by delta VR. This is called the Clausius-Clapeyron slope. Clausius-Clapeyron equation. It gives you dP by dt, it gives you the slope of a reaction in temperature pressure space. And that is given by delta SR and delta VR, where the entropy change of the reaction and the volume change of the reaction. Now we have been discussing that the delta VR is a very small number. So if this is so, then this ratio is going to be very large because delta VR is a very small number tending to 0. So what happens? These reactions have a very steep dP by dt slope, or drawn in the diagram they can be like this. That means dP by dt here is almost infinity. That means delta VR should be very close to 0. Or you would have these expressions like this. Here delta P by delta T is steep but has a positive slope. Or you could have a slope like this, where dP by dt is still steep but the slope is negative. That why positive and negative? This would depend on the signs of delta SR and delta VR. The signs will give you, the steepness will give you by the ratio of the number, but the signs of this delta SR and delta VR, it will tell you what is the direction of the slope. This is a very little point, but the point that is important is these reactions or NGFE reactions and cation exchange reactions have a very, very steep slope. Have a very, very steep slope. This is one point I had to make. And the second point you can see better from ideal exchange reactions. You will see that at a particular temperature, say for example, if we ignore this term at the moment, it's creating a little confusion, whether it will be positive, a little bit negative. So if we make it just 0, then that element goes. So now you see, and this term is called, we have called this term KB. Now you can see, for a particular temperature, if delta VR is 0, then the slope will be vertical. This should be equal to a particular value of KD. Say KD1. But if you change the temperature, this ratio will change. So you will have another temperature, you will have KD2. Or another temperature, it will be KD3. So what is happening? The steepness of the reaction is the same, but the position of the exchange reaction or the PT locus of the exchange reaction would be a function of the ratio of the compositions of biotite and garnet. Or looking at another way, depending upon the temperature, KD will have a unique value. So every line would be characterized by a particular KD value. And this reaction line will have a very steep Clausius-Clapeyron slope, because delta VR has only a very, very small value. So we conclude this by saying that we realize that yes, the exchange between cations, between phases, can be thermodynamically modeled. If you extend your vision a little bit further to core mantle structures, to crust mantle structures, to crust mantle interactions, you could imagine that the partitioning of a particular element during mantle melting to the melt would also depend on the pressure temperature conditions. And also, if the system is non-ideal, it would also depend on the composition of the rock itself. So, what I'm trying to say, that even this reaction tells you that, okay, if there is a mantle melting into the crust to form the crust, then for mantle melting, the temperature and the pressure and even the composition of the rock will determine how the elements are partitioned between a rock and a melt. Between a rock and a melt, how it is partitioned. And not only as a function of pressure and temperature, but for an ideal, non-ideal system, it is also dependent on the composition. So that is very important. So now we move into the orthopyroxene part. I will now, since I have already talked to you about iron magnesium partitioning between biotite and garnet, in the orthopyroxene there was this problem, that M1 and M2 sites that M1 and M2 sites were different in their size. It is also true that the competing cations, magnesium and iron, they were the occupants of the M1 and M2 sites. And obviously, because the crystal lattice, both of them you must understand, are octahedral coordination. I drew the details of that, so you know this by now. So you have a larger home and you have a smaller home, and you have a smaller cation and a larger ion cation to home. So what they do is, they are not, once again if I quickly draw the diagram, it is, it looks like this. XFE M1 is equal to XFE M2 site in orthoperoxide, and the diagram that was important to us was that the curves look like this. This was the direction of increasing temperature. The important point was, we always saw that the larger cation iron was partitioned into the M2 phase. That is why all the curves lie on this side of the diagram. So for a particular value of XFE M1, the amount of XFE in M2 is larger. Have you understood? So what is happening here is, we need to find out why this happens. The deviation is very large at lower temperature, but as we increase the temperature, we can see the Fe by Mg partitioning becomes closer and closer to the 1:1 line, which means if the line coincides with 1:1, which it does at around 1200 degrees centigrade, Bias and Kohn in his experiments have shown that at 1200 degrees centigrade, roughly around that, the FEMG partitioning lies on this straight line, which means at low temperature, XFE M1 is not equal to XFE M2 and is not equal to XFE orthoperoxide. But as we go high temperatures, or the highest temperatures, then XFE M1 is equal to XFE M2 is equal to XFE OPS. So this is called random on-site mixing. Random on-site mixing. That means neither the iron nor the magnesium has any preference for any of the sites at high temperatures. But at low temperatures, M2 sites are larger, and therefore iron prefers the M2 site rather than the M1 site. So you can understand now, we can write an equation of state which expresses the partitioning of FEMG between M1 and M2 sites. So we write an expression we write this equation. Fe in M1 plus Mg in M2 is equal to Mg in M1, Fe in M2. Which means here is the side part, is the partitioning of iron and magnesium in the M1 side, and here is the magnesium iron partitioning among the M2 side. So both M1 and M2 are the same on either side of the expression, but we are talking of iron magnesium partitioning between the M1 and M2 side. While doing this, what we have essentially, or the authors in their experiments, now their experiments were done at 1 bar pressure. 1 bar pressure was the experiment at which they done, which is the normal atmospheric pressure. So you can see we can neglect the effect of P into delta V. We can neglect the effect of P into delta V for the simple reason the pressure is very low and that term is not going to contribute significantly to anything. So we will not take in the P delta VR term when we are dealing with exchange reaction, simply because it is an additional term, it adds nothing additional to the exchange, thermodynamics of exchange. Now, before I go into the details, I should tell you that this iron magnesium partitioning in orthoperoxene and olivine has been done by many famous people. Over time, there has been many famous people, starting with Saxena and Ghosh himself, Virgo and Hafner, then you have Besenkorn. A whole set of authors have worked on this system using Mossbauer spectroscopy, etc., etc., etc. And they have come to very convincing results. There might be some discrepancy, but their results are mutually compatible. You know, they have done their work over a spread of 40, 50 years. During this time, experimental accuracy has increased considerably. Softwares have developed which have improved detections, analysis, synthesis, whatever it is. So there is some problems here and there, but overall, if you take the overall grid, there is not so much of a mismatch. Not so much of a mismatch. Now, what do their data have? As I told you, they estimated whatever estimations they could have done. They have done it at 1 bar. So what is the basic data they have? They have what is called a temperature, a column of temperature. Then they have found out XFE in the M1 site. That means they have found out how much Fe is there, how much Mg is there in the M1 site, and if there is so much Fe and so much Mg, then you can find out what is XFE M1. They have also found out XFE M2 using this Mossbauer spectroscopic method, which allows you to find out the occupancy of iron and magnesium in simple orthoperoxene and even olivines. So they have found this. And then they have also found out the composition of XFE orthoperoxene. So they have found out the XFE of orthoperoxene, they have found out XFE in M2 side, and they have found out XFE in the M1 side. When you say XFE, they found out both iron and magnesium. Here also they found both iron and magnesium. Here also both iron and magnesium. So say for example, say the temperature is 800 degrees centigrade, which means essentially say they start an experiment at 800 degrees centigrade, which means 1073.15 kelvins, where they find out a value of XFE M1, another value of XFE M2, and the value of XFE orthoperoxene. At another temperature, they take another orthoperoxene and find out the data. At the same temperature, for another orthoperoxene, they find out this value. And then, for example, they do 1000 degrees centigrade, and that means 1273.15 kelvins. And again, they go on finding the different values. Have you understood? So this type of experiments they have done in a range of 600 degrees centigrade, where the experiments are less and the experiments are less accurate, because as the temperature decreases, this exchange or diffusion of iron magnesium becomes sluggish. So what happens sometimes, equilibrium is not established. But at temperatures above 700 degrees centigrade until about 1200 degrees centigrade, the experiments are much better constrained, the results have much more accuracy, especially at high temperatures, the experiments are deadly accurate. So this is the data we have. We have data on temperature, we have data on XFEM1, we have data on XFEM2, and we have data on XFEOX. We also have data on pressure at 1 bar, but we choose to ignore that 1 bar pressure because we know P del VR will only be a small contribution to the whole energetics of the turbine. So, to start with, so this is our data, essential data that we can use to handle, and I will show you how it is done. So, the important expression here again, like before, and this time I am writing it all at one go, so that, because you already know biotite carbon, so it's just a transformation of phases. So thermodynamic equations don't change depending upon the reaction. It changes depending upon your approximations. They are very unique expressions of state. So you have delta GR of the reaction, obviously at a particular temperature. I'm ignoring pressure because that effect we have taken out. And this will lead to del GR 0 plus RT ln KD. What is KD? Now immediately you can write down KD. This is not a physical class, although I've asked you to detail it. It would be xmg by x Fe xmg. So it will be, if I write it normally, it will be x mg m1 into x mg m1 into x Fe m2 divided by x Fe m1 into x mg m2. And this we can write as before, x mg by x Fe m1 divided by x mg by x Fe m2. So now we have, therefore, our KD term for the expression is xmg by x Fe m1 divided by xmg by x Fe m2. This is our expression. I will write it down because this class will continue to the next class and I will forget. So I will write down this expression. So now I erase this part. And this is RTL and KD plus now you have RT ln gamma Mg by gamma Fe m1 minus RT ln gamma Mg by gamma Fe m2. This is the equation of state. delta G0R plus RTLN KB, which is the distribution coefficient as given here, plus RTLN gamma mg by FEM1 minus RTLN gamma mg by gamma FEM2. This time there is no 3 here like last time because the mixing is on one side. Have you understood? And the stoichiometric coefficient is always 1. So that is why. Now at equilibrium, delta GR is equal to 0. And this term, delta GR, if you omit P delta VR, then this terms become delta HR0 minus T into del SR0. This is this term. We have not taken P delta VR0 term because that term we have neglected because the pressure is very low. Then the term plus RTLN KB plus. Now what will I write? See if I have done a mistake or no. FEMG M1, and it should be 1 minus 2x mg m1. You can check it out. Minus WFEMG m2 into 1 minus 2x mg m1. I think I have done right, but you please check it out. So this is the expression now for MgFE exchange between M1 and M2 side of the peroxide. Del HR minus T del SR plus RTLN KB, partition coefficient. We have taken a simple regular solution model. You can ask me, sir, what happens if WFEMG is 0? You will see that if WFEMG is 0, it will come out 0. Then we will know it's ideal. It will come out 0 when we go to the next step. But I think I will stop here today because the next step will take me further away, and I will take about another 25 minutes to conclude, 20-25 minutes to conclude this. So I will as well conclude this now. And we come then to the end of the 9th lecture in the 3rd week of this semester. And I will soon today, definitely by today, I will upload it. And the time has come to take an exam now. So I will let you know in the post in the Google Scholar what happens to it. Okay, thank you very much.